Okay, let's go ahead and get started. The lecture on Tuesday was the last lecture on randomized stuff for a while. I'm hoping that we'll see a little bit more of it at the end of the semester, but for now, that's all I wanted to say, which means we are now halfway through the course. There's 4 big chunks to the course. There was the first chunk, which was on dynamic programming, the second chunk, which is on randomized algorithms. The third chunk is on something called combinatorial optimization, and then the fourth chunk will be proving and dealing with hardness. So for the combinatorial optimization part, at least starting out, we're back in the realm of you have the entire input given to you at the beginning of the algorithm. There's no streaming or anything. I want an exactly optimal correct answer all of the time. I'm not going to be applying randomization in the algorithm. I'm not going to allow, you get the right answer 99% of the time. We're back in the sort of traditional role of algorithms that you saw in 225 and 374. And the particular problems that I want to start with are graph algorithms. Now these are going to be a slightly different style of graph algorithm than what you saw in 374. So previously you have hopefully seen how to do things like decide if there's a path from one vertex to another, so-called reachability. In an unconnected graph, you know how to count how many components there are. You've seen already topological sorting for DAGs. You probably know how to use at least one algorithm to compute shortest paths. You probably know at least one algorithm to compute minimum spanning trees. These kinds of problems, the output of the thing you're trying to compute is either a subgraph, a shortest path tree, or a path, or a spanning tree. Or it's, for topological sorting, it's an order. It's a nice discrete thing. For at least one of the 2 problems that I want to introduce today, the so-called maximum flow problem, the structure of what exactly you need to compute is a little bit different than what we've been used to. Essentially, what you need to compute is a weight to assign to every edge, where these weights need to satisfy certain constraints. So I want to start off with this map, which comes from an internal Army think tank technical report written around 1950, which was sort of at the height of we just got out of World War II, and oh crap, the Russians are evil. So okay, we just got done with Hitler. Now we've got to deal with Khrushchev. So the army was tasked with, coming up with plans to defend the upstanding countries of Western Europe a bit against the Red Scourge from Moscow. And so part of that report, Harris and Ross, who were Air Force researchers, built this graph, which is nominally a map of Easternish Europe. So, for example, this region down here, labeled H, that's Hungary. Here's Romania down here. This is Austria over there. And basically, rather than building a model of the entire Warsaw Pact rail network, they abstracted it somewhat into having a node for every major region of Eastern Europe. So some of these regions correspond to individual cities. So this node up here labeled EG, that's really Berlin. But it stands as a proxy for East Germany. 1, 2, and 3 are essentially, Vienna, Innsbruck, and Graz, I guess. This is Bucharest. Maybe that's Bucharest. So between the nodes representing these regions in Western Europe, they drew edges that represent railway connections. And attached to each of these railway connections, I'll zoom in a little bit so you can see this, they added numbers. These numbers in the boxes represent how many trains can go from one city to the next in a single day, or what's sort of the steady state rate at which cargo can be transported between these two regions along the railway connections between them. And then the question was, suppose that I want to ship equipment or soldiers or vodka or some other resource from these nodes over here on the right, which are labeled origins, and I want to ship them over to, say, East Germany, here. Okay. Now, the numbers that are attached to the edges indicate how much flow can go across that edge in sort of a steady state rate. If I want to think of this as, I've built the great vodka pipeline network here, and I'm pumping, thousands of liters of vodka through Eastern Europe. I can, in principle, push 52 megaliters per second between these two cities, but all the vodka has to go in at the origins, and it all has to come out in East Germany. So there's a constraint that whatever flows into the city has to flow back out again. And so if you look at the numbers that are attached that are not in the boxes, for example, if you look at the numbers into and out of this vertex labeled 5, I've got 34 megaliters per second coming into city 5, 12 of them leave to the west, and 22 of them leave to the south. There's another link going up to the northwest, but there's nothing traveling along. In every case, the number that's not in the box, that represents the actual amount of material flow across that link, is smaller than the so-called capacity of that, which is the number in the box. It's also, but there's a second constraint, which is that except for the sources and the destination, whatever material flows into any other node must also flow out. So I have a linear constraint that says if I've got a certain amount going into this vertex, that exact same amount must go out of that vertex. And then the question becomes, what is the maximum amount of vodka that I can push from Moscow to Berlin? And so Harris and Ross sat down and they figured this out by hand, and they came up with this map. Of course, they were thinking about soldiers and guns and nuclear missiles rather than vodka. It turned out it's actually possible to make vodka in East Germany. But then the second question comes up, which is to say, suppose we wanted to, say, destroy some railway networks so that it becomes impossible to send nuclear missiles from Russia into East Berlin. And so Harris and Ross identified in their map, there's a dashed line here, which you'll notice they refer to as the bottleneck. This is the line that they said, you know what, if you'll notice, every link that goes across the bottleneck is completely full. I've got a capacity of 36 and I'm sending 36 units of flow. Here I've got a capacity of 24, I'm sending 24 units of flow. Here I've got a capacity of 6, I'm sending 6 units of flow. Okay? And the bottleneck is also what they identified as, if you were going to blow up a small subset of the railway network, those are the links that you would want to blow up. Okay, and now I'm assuming that if I've got a capacity, say, of 36, that means I've got 36 independent railway lines going between those two cities, and so I'm going to have to drop 36 bombs in order to blow them up. So when I say this is the cheapest way of disconnecting them, I'm taking these capacities into account when I compute the cost. More things with larger capacities are going to be more expensive to destroy. Things with links with smaller capacities will be less expensive. So this is the first sort of published example of the two problems that I want to talk about, which are the maximum flow problem and the minimum cut problem. How much vodka can I send from Moscow to East Berlin? And how few pipes can I blow up so that no vodka gets from Moscow to East Berlin? This particular map and the technical report that went with it was classified until 1999, which means, after I was, after I'd already been here on campus for a year. Of course, by then, everybody knew what maximum flows were. The wall in Berlin had already fallen 10 years previously, but it still took somebody to actually go and ask. I hear there's this rumor of a paper by Harris and Ross that some people refer to. Could I see a copy of it? And after a couple of years, the Air Force said, well, okay. All right. So what is the problem, in the abstract? Okay. So here I've got two copies of exactly the same input graph. The input. Sorry. Hey, come on. The input. Excuse me. I need to charge my doohickey here. The input consists of a directed graph. Actually, in the Harrison-Ross example, it was an undirected graph, but it's a little bit easier if we give the edges directions. So there's a directed graph with two special vertices. There's a source vertex called S, and there's a target vertex called T. In the example that I've drawn on the screen, S has only outgoing edges. It's a source, and T has only incoming edges. It's a sink, but that's only for this particular example. In general, there may be edges going into S, and there may be edges going out of T. It's just an arbitrary directed graph where I've identified two special vertices. And in addition, every edge in this graph has a number associated with it, which is called the capacity of that edge. Okay, so for some reason my my fancy Apple toy is not working, so we may have ugly slides today. Fine, we'll do it the hard way. So we have a graph G, vertices and edges, and we have a function that maps every edge to a real number. That function is called the capacity. Okay. I really, really hope to fix this. I may have to unplug the screen here for just a second to repair the pencil, but I'll try to go on as much as I can. Okay, so what we want to compute, there we go, is a function f from the edges, again, to actually not the positive reals. It's possible that I could output 0. This is called the flow function. And the flow function satisfies a couple of different sets of constraints. Right? So one constraint is capacity. For every edge, the flow has to lie strictly between 0 and the capacity of that edge. And I'm going to use this this notation, U arrow Q, that's a directed edge from vertex U to vertex V. And then there's a second constraint called conservation. Sometimes it's called balance, which says that for any vertex V, the sum of the flow values on edges going into V is equal to the sum of the flow values on edges going out of V. For all V except the source and the target. Okay? So the way that I'm going to indicate the flow function in my figures is I'm going to write what looks like a fraction, but I'm always going to draw this as flow over capacity. Okay? So here is a legal flow in this graph. 0, 0, 10, 5, and that's supposed to be out of 10, not out of 20. 5 and 5. Okay, so if you'll notice, for example, the vertex in the lower left has 10 units of flow coming in from above, and it sends all 10 of those units out to the right. The vertex in the lower right has 10 units of flow coming in from the left, and it sends 5 of them straight up and 5 of them over to the target. The vertex on top has 10 coming in and 10 going out. The vertex on the top right has 5 going in and 5 going out. The source has 10 units of flow going out and none coming in, and the target has 10 units of flow going in and none coming out. And that's not a coincidence. All the flow stuff that comes out of the source can't get stuck anywhere else in the network, so it must eventually find its way to the target. Okay, so I'll have a certain amount of excess flow coming out of the source and a certain amount of excess flow coming into the target. And that number, the amount of flow going out of S and the amount of flow coming into T, that's called the value of the flow. And this is the objective that I'm trying to make as large as possible. So I want to maximize the flow value, which is defined as the total flow out of S minus the total flow into S. Or it's defined as the total flow into T minus the total flow out of T. I think I need to make a little bit more room here. I'm just going to do this the easy way. Okay, so here's a graph, and here's a flow. Hopefully it's easy to see that this flow satisfies the capacity constraints, satisfies the balance constraints except at S and T. And in this case, the value of the flow is 10. Yeah? Can
you explain what you're saying with maximizing?
Okay, so I want, essentially you should imagine that I'm injecting stuff into the system at S, and I'm ejecting stuff out of the system at T. And so what this objective function represents is the amount of stuff I'm putting in at S and taking out at T. That's what I want to, when I say maximum flow, that's what I'm actually trying to maximize. Okay. So, as a sanity check, is this a maximum flow? Yeah, there's another question? Yeah, I'm sorry?
Why don't we just command stuff pushed into the flow? Why do we not comment how much is getting out of that? I mean, why can't we?
Because that's the definition. I mean, the answer is that what you should really imagine is stuff is coming into S from that little arrow that I've drawn on the left. But there might be another edge from T to S. And that edge from T to S might carry flow. But that should somehow count. If I'm spewing out 10 megagallons of water an hour, but somebody else is pouring a gallon of water on my head every hour, that should count against the amount that I'm distributing, right? So it's really helpful to think of the substance that's flowing around here as water. And what I really mean is I'm going to attach a hose over here, and water is going to spew out over there. How much water can I push through the system? And if some water manages to flow back to S, that water is still going to have to go somewhere, and it's still going to impact the total flow value. Now, it is true that every graph has a maximum flow where nothing flows into S. You can always find a way of sort of canceling that out, and we'll sort of see how that works later. But the definition allows flow to go back into S. Okay? So, is this a maximum flow? No. Why not? Can I push more stuff through this graph? So how would I do that? Where would I push the flow through? Right, so I could push more flow along this path. And if I decided, how much more flow can I push along that path? 5, because the bottleneck in how much I can push through is, well, I've got 10 spare units of capacity over here on the left, and I've got 10 spare units of capacity over here on the right, but I've only got 5 units of capacity in the middle. So I need to change this to 15, 5, and 10. Okay? Now, it turns out that is a maximum flow. And you can stare at it for a while and realize I don't see any other way to push flow from S to T, but that's not a proof. I need an actual way of proving that it's a maximum flow. So it's a good time to think about what the minimum cut problem is. So the input to the minimum cut problem is exactly the same. It's a graph. It's the same graph. It's still got a source. It's still got a target. It's still got whatever. It's still got capacities on the edges. But now the goal is to figure out a way of separating S from T. And so what I'm going to do is say, okay, here's a subset of vertices containing S. Here's the complementary subset of vertices containing T. And this pair, capital S and capital T, define a cut. I can do better than that. Okay? So an ST cut is a partition of the vertices into 2 sets. One set capital S that contains the source, and another set capital T that contains the target. Okay? Every vertex was in exactly one of these 2 sets. That's what the word partition means. And then the capacity of the cut, the cost of the cut, the value of the cut, which I will write using notation that I made up. This is defined to be the total capacity of all the edges that start in set S and end in set T. Okay? So let me write this way. The sum over all vertices U in set S, sum over all vertices V in T, of the capacity of the edge from U to V. This is the definition of the capacity of a cut. So, in particular, this cut has 5 edges crossing it, 10, 10, 15, 20, and 15. But notice the 20 is going backwards. It's starting in T and ending in S. So the capacity of this particular cut is 10 plus 10 plus 15 plus 15. In this case, the capacity is 50. When I talk about the minimum cut problem, I want to find a cut where this objective function is as small as possible. Okay? Now, it's quite possible that these cuts look very, very simple. So I'll show you this, for example, is not a minimum cut. It's not even close. So I'll show you a better one. Okay, I just take S itself to be the source side of the cut and everything else to be the target side of the cut. And if I do that, the capacity of this cut is only 30. Okay. Is this a minimum cut? No. So can you tell me where I might find something better? So just cut straight down the middle. And now, this is really annoying. Hang on just a second. I'm sorry, I need to try to reset this. So we're going to have a short break, but what's the capacity of this cut? 15, right. 15. All right. Now I want to point something out, just pictorially before, while I'm fiddling with my stupid little devices. At the top of the screen, I have a flow with value 15. I can successfully send 15 units of stuff from S to T through this network. At the bottom of the screen, I have a cut with capacity 15. If I destroy a total of capacity 15 of edges, namely these two that are going from left to right across the middle, then I've removed any possibility of pushing flow from S to T. Now, the first sort of non-trivial observation that I want to make is, because these two values are equal, I claim that that is a proof that the flow at the top is a maximum flow and that the cut at the bottom is a minimum cut. Intuitively, I can't make the flow bigger because whatever stuff flows from S to T has to flow from capital S to capital T. It has to flow across this cut. But I can only push 15 units of stuff across this cut. Right? Conversely, if I ever found a smaller cut between, separating S and T, it would still have to have enough capacity to allow 15 units of flow to go through it. Okay? So this is what's known as the easy half of the Maxflow mincut theorem. It says that if I have a flow whose value is equal to the capacity of some cut, then F is a maximum flow, and ST is a minimum cut. Minimum spelled with an M. Okay? So intuitively, this is clear, but I want, just because these definitions are At least I found them when I first saw them a little bit unintuitive. I want to walk through the definitions, walk through the calculations just a little bit carefully. And the way that I'm going to do this is to start by proving something simpler. So the claim, the lemma. Does anyone know what the difference is between a lemma and a theorem? Lemma starts with L. It comes from the Greek word meaning helper as opposed to theorem, which comes from the Greek word meaning theorem. Okay, so let F be any flow, satisfying all the balance constraints and capacity constraints, and let ST be any cut. Then the value of the flow is at most the capacity of the cut. Okay, and I claim that once I prove this lemma, this statement about if I find a flow and a cut that are the same value, then the flow must be maximum and the cut must be minimum. And the basic idea is I have this sort of range of values that I can think about. And no matter what flow I find, its value is going to be higher than whatever cut I find. Okay? So I want to, I mean the other way. Yeah. Okay. Fine, we'll do this easy way. You can't do this on a, can't do this on a blackboard. Okay, so I want to push the flow higher. If there's a gap in here, then there's at least the possibility that I might be able to push the flow higher. And similarly, I want to push the cut downward. But if it just so happens that the flow and the cut coincide, then I can't push the flow higher without violating this inequality. I can't push the cut lower without violating that equality. All right. So, proof. This is really just going to be an exercise in definition chasing. So let's just write down what the value of the flow is. This is the total flow out of S minus the total flow into S. That's just the definition. Okay? Now I'm going to add a bunch of zeros. Okay? And namely, what I'm going to do is I'm going to say this is equal to the sum over all vertices on the S side of the cut of the total flow out of V minus the total flow into V. Now, I claim that I've just added a bunch of zeros. So one of the terms in this sum is when V is the source vertex. That's already written up here. For every other vertex on the source side, because of the balance constraint, this expression is equal to 0. So I've just, that equal sign is because I just added a bunch of zeros because of balance. This is by the definition of the flow value. Okay? Now, I want to delete a bunch of zeros. So I'll notice that if I have an edge where both endpoints of the edge live on the source side of the cut, that edge appears in this expression twice. Once as positive flow and once as negative flow. The only edges that don't appear twice are the ones that have one endpoint in S and the other endpoint in T. If an edge has both endpoints in S, it's going to show up, if I have an edge from X to Y and both endpoints are in S, at some point V is going to be equal to X and W is going to be equal to Y, and then later V is going to be equal to Y and U is going to be equal to Okay. The only way I don't get anything canceled is by saying, actually, I only care about W and U if they're on the T side of the cut. Okay? So all this is removing duplicates, which are sort of cancel each other. I'm again just removing a bunch of zeros. Okay. Now, if I look at, let's see, I'm going to make sure I get this right. If I look at this term, f of uv by the capacity constraints, f of uv must be greater than or equal to 0. So I claim then that I can just remove this interior sum entirely, and I've only made the expression bigger because I've decided not to subtract something. Okay. So this is at most, this is at most sum of V in S, sum of W in T, the flow from V to W. And the reason is that flow is always non-negative. On the other hand, I also know something about this flow value, which is that it must be less than or equal to the capacity of the corresponding edge. It's the other half of the capacity constraints, sum over V in S, sum over W in T of the capacity of the edge from V to W. And this happens because flow is less than capacity. But this last expression is equal to the capacity of the cut from S to T because that's the definition. Okay? Definition, add some zeros, subtract some zeros. Definition must be positive. Definition must be less than capacity. Definition. Now, there are only two places where I get actual inequalities. One of them is in this first step. If any of these flow values that I removed are positive, then this is a strict inequality. And what that means is, if there's any flow going backwards across the cut, then I get a strict inequality here. On the other hand, the other place I get an inequality is if this flow is actually less, any forward edge going forward across the cut isn't completely full. Okay? So I can sort of strengthen this by saying, sort of a corollary. The difference, by the way, between a lemma and a corollary is that a corollary is not from a Greek word and it starts with C. For some reason, lemmas come before things and corollaries come after. If the flow from UV is equal to 0 if U is in T and V is in S, and it's equal to the capacity if U is in S and V is in T, then the flow value is equal to the capacity constraint, and F is a maximum flow, and ST is a minimum cut. And in fact, this, if you walk through the math even more carefully, this is an if and only if. Right? So if I have a flow and I have a cut, they're going to have the same value if and only if they satisfy this condition, that if I look at any edge crossing the cut going forward, it's completely saturated, it's full. The flow value is equal to the capacity. And if I have any edge going backwards across the cut, it's completely empty. And so as a sanity check, let's look at the example that we had before. I have two edges that go forward across the cut, one with capacity 5 and one with capacity 10. And sure enough, I'm sending 5 units of flow across the top edge and 10 units of flow across the bottom edge. I have an edge that's going backwards across the cut that has capacity 15, and sure enough, in the flow, I'm not sending anything across that. And so here I have a certificate that I am done. I have in fact solved the problem for this particular graph. And I use this language accurately. Notice I said I've solved the problem. Because one of the things that this argument implies is whatever the answer to the maximum flow value problem is, it's the same number as the answer to the minimum cut problem. So I think this is a good time for me to stop and make sure that this fire hose of definitions is starting to sink in a little bit. Are there any questions about this? Yes?
What are some other applications of this?
Okay, what are some applications of this? So cuts, for example, show up in image segmentation problems. So I have an image that I've taken with the camera on my phone. I somehow have some prior knowledge that pixels near the bottom of the image are likely to be in the foreground and pixels at the top of the image are likely to be in the background. And you can think of the weight of an edge as like how similar are the colors between these two pixels. And now what I'd like to do is draw a boundary between the foreground and the background, segment the edge into smaller pieces, in a way that sort of makes probabilistic sense. And then it turns out to be equivalent to minimizing the cost of the edges that you cut. In that case, actually you have to imagine every edge as being directed both ways. So you don't have this distinction between forward and backward. Yes?
Can you just scroll down to that?
Sure.
Thanks.
Right. This is verbatim from the lecture notes, by the way, so if you want to follow on at home later. Okay. Flows, we'll see a couple of examples of where flows show up. But it turns out that flows are a sort of canonical example of doing kinds of resource distribution. I want to plan out, how to move packages from from Amazon to your house. When you order, Amazon has to do these kinds of flow computations all the time when it's planning out, how its fleets of planes and trucks are going to drive around. But as we'll see sort of later in the semester, it's also good for things like what are called matching or assignment problems, where I need to pair things up in a way that is as good as possible. So I have exams and I need to hold them in rooms, and I can't have more than one exam in the room at a time. And the exam has to be held in a room that is big enough to hold all the students. And I want to assign as many exams to rooms as I possibly can. That turns out to be a problem that one can solve with maximum flows. But like I said, we'll see lots of other problems like this in the next few weeks. Okay. All right. Now there is one small bit of gap in the argument that I've tried to give here. What this says is if I can find a flow and a cut that match in value, then I know they're both optimal. It's possible in principle, and we'll actually see examples of this near the end of the semester, where I can't actually, there might not be a flow and a cut that have the same value. There might always be a gap. It may be that the maximum flow has value 10, the minimum cut has value 12, and I'm sorry, but you just can't do any better than that. Okay. In this particular case, that can't happen, because the only way to get the flow, and well, actually, this argument isn't going to do it for me. I'm going to have to actually prove that separately. That, in fact, I can always find a flow and a cut that match each other in value. And so to do that, I need to go back to my original flow. Go down to the next page and describe an actual algorithm. So I'm gonna imagine that I'm jumping into the middle. I've already computed part of the flow. I want to complete it into a maximum flow, and I want to think of this as usual when I'm thinking about recursive algorithms, as I want to make some improvement in the flow, and then let the recursion fairy take over. Right? If I can make some measurable improvement, if I make the flow value go up, then I can then recursively maximize the flow in what I have left. So make a little bit of progress, and then I'm just going to put this in a loop. Progress over and over again. In this particular example, we could just eyeball it. We can see that there's flow that can go through the top of that path at the very top. But in general, we can't eyeball it. We just have a data structure, some adjacency list that at every edge record I have a capacity and a flow value stored. I need an algorithm that can actually figure out whether there's a way to get from S to T. And one thing to actually think about here, let me make sure that I have an example where this is actually necessary. Let me suppose, for the sake of argument, that that edge has capacity 5, not 15. And so now that top path doesn't actually work. Right? It doesn't have any, I can't send any flow through it. No, that's not good enough. Rather than coming up with an example, maybe I should just tell you the algorithm. So the thing that, when you eyeballed this, what went through your mind was probably something along the lines of, well, I can see those top 3 edges. I still have capacity going forward, so I'm going to use more of it. Yes, that's the one I want to change. So let's suppose that instead of 20, this edge had capacity 10. Okay? Now, in this case, if I just try to push more flow through the edges that I can see on the screen, I can't go up from the source because that edge is completely full. I can go down from the source, but then I can't go any further because the edge leaving here is also completely full. I have a flow value of 10, but in fact I claim this is still not a maximum flow. There's a trick that will allow me to push a little bit more flow through this graph.
You want to redirect that middle edge to the top and push more to the top.
This edge here? Okay, so essentially what I'm going to do is, instead of adding flow to an edge going forward, I'm going to imagine subtracting flow from an edge. So I claim I can push more flow through this graph by following this path. Now this is a bit weird because the second edge in this path is pointing the wrong way. But intuitively what I'd like to be able to say is I can push 5 more units to the first edge, 5 fewer units to the second edge, 5 more units to the third and fourth edges. So the way that I would do this algorithmically is I would build something called a residual graph. The idea is, here's S, here's T. I'm going to replace every edge with a pair of edges where I'm going to define something called the residual capacity of an edge. This is either going to be the capacity of the edge minus the flow through that edge, if UV is actually an edge in the original graph. So the residual capacity for that particular edge is going to be 0. That's if UV is an edge in the original graph. Otherwise, it's going to be the flow through the reversal of the edge if V to U is in the edge. So here I have 10 units of reverse residual capacity. Okay, so here I have 5 going forward and 0 going back. Here I have 10 going forward and 5 going back. No, stop that. Here I have 15 going forward and 5 going back. Here I have 0 going forward and 10 going back. Here I have 10 going forward and 0 going back. 0 forward, 10 back. 5 forward, 5 back. 15 forward, 0 back. Okay, same source, same target. And now, to keep things somewhat sane, if an edge has residual capacity 0, I'm just going to remove it completely from the graph. Okay, so in this case, some pairs will still live. So over here on the right side of the graph, where the edges in the original graph are neither empty nor full, I'll have both edges and their reversals. Over here on the left, I'll either have the forward edge, for example, this 5, or I'll have the reverse edge, but not both, because the edge that I've deleted had no capacity left. And now this thing that I outlined in orange on the top, if I do that again, this just corresponds to a path in the residual graph. Okay, so this is called the residual graph. It's sometimes called G sub F, where F is the flow in the original graph. This is the original graph G. The numbers are, the flow values are F. And the way I define the residual graph is I put in the reversed edges, I define this new capacity function, and then I delete anything that has residual capacity. Okay. So the first thing to observe is if there is a path from S to T in the residual graph, then I do not have a maximum flow because I can push more flow along that residual path, along that path. Okay? Every path in the residual graph corresponds to something that looks kind of like a path in the original graph, except sometimes the edges are backwards, where I can push more flow. Adding flow if I'm moving along the forward edge, subtracting flow if I move along the edge backwards. Okay? So if G sub F has a path from S to T, then F is not a maximum flow. I can increase the flow value by what Ford and Fulkerson called augmenting along that path. Okay? Now, this is a question that you can now answer algorithmically using tools that you learned in 473. Given the vertices and edges of the graph, given the flow values and the capacity values, you can construct the residual graph in time proportional to the number of vertices plus the number of edges. It's just, you just do it. Right? And then if I want to know whether there's a path from S to T, that's a standard reachability question which you can answer with whatever first search, starting at S. Breadth first search, depth first search, it doesn't matter. Okay? So this is something that you can test in order V plus E time. Moreover, if there is a path from S to T, how much flow can I push along? How much flow can I add to the original flow?
Smallest number.
Right. It's the edge with the smallest residual capacity is the one that determines how much flow I can push through that path. Okay? So I can now, let, let's call it capital F be the minimum of the residual capacities along that path. And now I can add, well, I'm abusing notation here. I can imagine the path itself as being a flow of value 1, and I'm going to, what this bizarre notation means is the way I get the new flow F prime is for every forward edge on the path, I'm going to add capital F. For every reverse edge on the path, I'm going to subtract capital F. And for every edge that doesn't touch the path at all, I'm not going to change the flow value at all. Okay, I'm going to do this. And now I have a new flow. And the value of the flow has gone up by this value capital F. Okay? So as long as I can build a residual graph, find a path from S to T, augment. Build the residual graph, find a flow from S to T, augment. Build the residual graph, find a path from S to T, augment. Every time I do that, I'm increasing the value of the flow, making the flow bigger and bigger. Okay? Now, originally, the flow values are all 0. When I start this algorithm, I'm going to start with just capacities, and in that case, the residual graph is the original graph. It's identical. Because if I have a forward edge, the flow value is 0, so I just get the regular capacity. If I have a backward edge, then there's no flow value, so its residual capacity is 0. So this gives me an algorithm. As long as you can, build the residual graph of the current flow, find a path from S to T. If you find one, push, change the flow by that amount. Repeat. Okay. So this is the algorithm proposed by Ford and Fulkerson. All right, so originally I'm going to set F to be 0 everywhere, and then I'll just say while the current residual graph has a path from S to T, augment F along that path. Okay, so the while condition requires me to do this linear time construction in search of the residual graph. So, what happens if I don't find a path from S to T in the residual graph? I'm sorry? It's a maximum flow, but why is it a maximum flow? right? I mean, and the answer is exactly that. I mean, once you can't push flow anymore, you're done. You've got a maximum flow. But I need to actually prove that I have a maximum flow. So let me go back to my original example of a maximum flow, and I will copy that and go down here and paste it again. Now let me look at the, I'm sorry, I really should have prepared this in advance. I'm going to draw out the interesting part of the residual graph, which is the part in the middle. I'm not going to draw the other stuff out explicitly. Okay. The residual graph has other stuff going on outside of these middle three edges. So let me just erase the numbers because they don't matter. Okay. So I don't know what these edges look like, so it doesn't really matter. Okay. So here is a case where I cannot find a path in the residual graph from S to T. So if there's no S to T path, let S be the vertices that I can reach from little s. So in this case, I can reach those three vertices from the source. This is going to be my set S. And then I'm going to let T be everything else. This is an ST cut. Okay? Now, think about, there are two kinds of edges in the original graph. In the original graph, there are edges that went from S to T. All such edges must be full, because if they were not full, there would still be some residual capacity going from S to T, which means I could actually reach that vertex over in T, but that contradicts the definition of S. So all of the edges crossing the cut going forward have to be full. On the other hand, I have some edges in the original graph that go backwards from T to S. All those edges have to be empty, because if there were any flow going along that edge from T to S, that would correspond to a residual edge going backwards from S to T, but then I could reach further than to that vertex over in T, which contradicts the definition of S. So all edges from S to T are full. All edges from T to S are empty. And we already proved that if I have a flow and a cut that satisfy this condition, then F is a maximum flow. And incidentally, S and T are a minimum cut. So this is how the Ford-Fulkerson algorithm ends. I look for a residual path that I can augment. If I don't find one, then remember how I look for a path from S to T is I ran, say, depth first search. What depth first search actually does is it computes all the vertices reachable from S. If that set doesn't include the target vertex T, then I say not only do I have a maximum flow, but here's the S side of the cut. Yeah.
But this kind of contradicts with your example that you can have the gap between the cut and T flow.
No. I said in principle you might. We haven't proved that you can't have a. We need to prove that there's no gap, and I haven't proved that there was no gap.
So it means it actually doesn't have a gap.
That's right. I've just finished proving that in fact there is no gap.
Okay.
But that was a fact that I needed to prove. It wasn't something that followed from the earlier arguments.
All right.
Okay. All right. So Here's the forward focus and augmenting path algorithm. Does everybody see why, at least at an intuitive level, why it computes maximum flows, why it computes minimum cuts, and why the Maxflow and mincut problems are in some sense equivalent? Yes?
I'm still a bit confused as to why computing residual graph mincut leads to
Oh, okay. So remember that in the residual graph, if I only keep the edges that have positive residual capacity. In other words, if an edge is in the residual graph, I can push more flow along it. So if I find a path in the residual graph, I can push some positive amount of flow through every edge in that path.
What about the reversing of direction?
Right, so when I'm pushing flow along a reversed edge, I'm subtracting flow from the original edge.
Okay, by the operator.
Yeah, exactly.
And so instead of that path, what happens if it's like on the like second to last node, it goes down and then to T? Like,
So instead from here, I go down and then up.
yes, then how would that make, like if you were to try to argue it, then how would that make sense since like from that node from on, like,
Well, okay, so suppose, the question is, suppose I tried to augment here. This is a perfectly reasonable path from S to T. The minimum capacity along this path is 5. That 5 shows up in 2 places. Okay. So after I augment along this path, the top edge will be full, and the bottom edge, because I'm pushing the flow backwards, this edge, this vertical edge, in the original graph will be empty. Yeah.
So in the algorithm, every time you update the original one, you update the residual one.
That's correct.
Then what's the running time?
Okay, excellent question. So building the residual graph takes linear time. Finding a path in the residual graph from S to T takes linear time. Updating the flow takes linear time. The only thing that's in question is how many times do you need to iterate this algorithm? Okay, how many iterations do I need? And unfortunately, this is a bit of a subtle question. Okay, so let me make one somewhat artificial simplifying assumption. It says, if all capacities are integers, are ints, I don't know what's going on with this. If every capacity in the graph is an integer, then the first time I find a path to push flow along, the amount of flow that I can push along that path is a positive integer. It's positive because otherwise it wouldn't be in the residual graph, and it's an integer because everything in the residual graph is an integer. So if all the capacities are integers, then every time I augment by induction, I'm going to augment by an integral amount, and my residual capacities will still be integers. In particular, every time I augment, I increase the value of the flow by at least 1. Okay, so every iteration increases the value of the flow by at least 1, which implies that the total number of iterations is at most the value of the F star here is the flow that I actually output. It's at most the value of the maximum flow. So if there is a flow with value 329, I can guarantee that I will do at most 329 iterations. Okay. This is not a good bound. Okay. The reason why it's not a good bound is that if you think a little bit about how we normally like to analyze algorithms, we like to express the running time as a function of the amount of data you need to describe the input. Now in this case, the input has two parts. There's the combinatorial part of the input, which are the vertices and the edges, and there's the numerical part of the input, which are the capacities. And every one of these capacities is an integer, but the size of the data isn't the value of the integer, it's the log of the value of the integer. If I want to express a capacity of 2 to the 16, I need 16 bits, actually 17, but okay. So what this number is actually the value, it's not the log of the value, which means in the worst case, which is horrible. This is horrible, right? The worst case is really awful. Now, admittedly, the worst case is really artificial. In practice, this works great, right? And part of the reason why this works great is because you can apply some heuristics to do a little bit better. Instead of just finding any old path from S to T, maybe you can be a little bit smarter about which path from S to T you find. So just one sort of obvious heuristic is, let's find the path from S to T that carries the largest flow. And that turns out to be something that you can compute relatively quickly. Not quite linear, you lose a log. But then you avoid this exponential behavior in the worst case. Okay. But there's a sense in which this algorithm really sucks. At some level, when we're used to thinking about algorithms with graphs, or in general algorithms that deal with numbers, we'd like to abstract away all the messy nonsense about bits. We'd like to just say, these are two numbers, I want to sort this array of numbers, I just compare these two numbers, it's one line of C, so I think of that as constant. I want to build a minimum spanning tree, I need to do some comparisons and some additions. I want to run Dijkstra's algorithm. I need to do some comparisons and some additions. I don't want to have to think about the complexity of the arithmetic operations. I just want to think of them as numbers. And so I'm working in this abstract model of computation where doing natural things with numbers, addition, subtraction, multiplication, and so on, just takes constant time. Unfortunately, this argument about Ford-Fulkerson halting in a finite amount of time breaks down when the capacities are real numbers. And it doesn't just break down because the argument doesn't work. It's actually the case that if the capacities are real numbers, the algorithm might not halt. Okay? So I'm going to give you an example. I'm not going to go through the details because we're almost out of time. But if you're curious, I strongly encourage you to look at the notes. Okay, so these numbers, x is some very large number. This is a 1, this is a 1, and this is the golden ratio, 1 plus square root of 5 over 2. Okay. So flow comes in from the source and leaves from the target. This particular example, if you choose the paths that you augment badly, the algorithm will run forever. Now, can anyone tell me what the maximum flow value in this graph is? So I've clearly got a path with capacity x over here. I've clearly got a path with capacity x over there. And then there's this path in the middle that has capacity 1. So the correct answer here is 2x plus 1. And notice, it doesn't matter what x is. Right? This as long as x is, I think, bigger than 2, this is the right answer. But but it turns out that Ford-Fulkerson infinite loops, or it can infinite loop, and moreover, over time, the flow value approaches 4 plus square root of 5, which is less than 7. So not only do you run forever, but you don't even approach the right answer in the limit. You don't have a good approximation. It's just awful. It's bad. And the reason is because you're arranged for every time you make an improvement, you make an exponent, the size of your improvement shrinks exponentially over time. Now, why would you care about this, given that you can't actually do real arithmetic? Imagine that these were floating point numbers. If you implement this badly, you'll end up in an infinite loop where you say, yes, I can augment, and then you add the new flow values, and your flow values don't change because of round-off error. And you just end up infinite looping because precision. And your answer is nowhere near the right answer. Like I said, I'll let you I'll refer to the notes for the details for that. I need to let you go, but if you have questions, I'm happy to answer them afterwards. Thank you.
I'm just wondering,